是吧 Okay, hello everyone. Welcome to the morning session. I'm Yilong Wang from BIMSA. It's a great pleasure to introduce the first speaker of today, Professor Fan Wei from Duke University. She will tell us about graph homomorphism density inequalities. Let's welcome.
Can everyone hear me? Oh, okay, yeah. Thanks, Professor Yilong Wang, for the introduction. I would also like to thank the organizers for organizing such a wonderful conference with so many people attending. And in addition, I would like to thank all of you guys for being here early morning on the last day of this week. Okay, so all the other talks in the combinatorics session give very nice introduction and motivation at the beginning. So I will also spend the first 1/3 or a half of this talk giving gentle expository introduction about this field and then why I care about some of the problems. And I would also like to encourage all of you to ask questions in the middle if there's any. Okay, so in these worlds, we mostly have seen like large networks or large graphs. So throughout the talk, I'll just talk about graphs for networks. So graphs consist of vertices and edges connecting to them. And for this talk, it might be helpful to consider the edges of the graph to have edge weights, and it could be either positive or negative. So what are the properties of large networks? Of course, they are large, and what we want is we want to extract efficient algorithms to run on large graphs for practical reasons. So one thing we really care for this talk is about sampling. So what information we can obtain from sampling from this graph. So what do I mean by sampling? So it means mostly it means different for different types of graphs. But for this talk, I'm mainly going to focus on dense graphs, meaning so if I have graph on n vertices, then the average degree in this graph is constant times n, or the total number of edges is some constant times n squared. So in this case, when I say sampling, it basically means what happens in this picture. So you pick uniform at random some subset of the vertices, and you want to look for whether there are edges existing between pair of vertices that you sampled. So notice this type of sampling doesn't really make sense if my graph is very sparse. For example, if my graph only has constant degree, because in that case, with high probability, the sampled subset of vertices doesn't consist of any edges. So you basically only see an empty subset. But it makes a lot of sense if we are talking about dense graph. Okay, so now I'm going to define probably the yeah, it appears in the title, but this is one of the most important definitions for you to understand this talk is the graph homomorphism density. Okay, so what do I mean by that? So formally, its definition, for the definition of a homomorphism number from a graph H to G is the total number of mappings from vertices of H to vertices of G that preserves edges. So the mapping doesn't have to be injective. The mapping doesn't have to be one-to-one, for example, and is roughly the subgraph count. So let me just give a quick example of what this means. Suppose my graph G is this graph, and my graph H is a triangle. So by the definition, homomorphism from this triangle to this G, you're just counting how many triangles here, basically. So there are 2 of them, and you're multiplying by the number of ways for you to label the 3 vertices of a triangle. So it's 3 factorial. Yeah, so basically the most important thing is you're counting the number of the patterns in this graph. Yes, you allow that. Yeah, so so for the ones you have to map non-edges to non-edges, those are called induced mappings. I'm not caring about that now. Yeah. Yes, you do allow that. Yeah, you can map to. So for example, if H is a wedge, it's like this thing, you can clap the other into one single edge. Yeah. Yeah, so those are great questions. So it means you guys understand the definitions already. So now I'm going jumping to the next definition, which is the homomorphism density. So this is nothing more than a normalized count for the homomorphism number. So what it is you're basically dividing the homomorphism number by the total number of mappings from vertices of H to vertices of to G. So in this example, there are 4 vertices in G and 3 vertices in H. So each vertex of H has 4 ways to map to in G. So the denominator you have is 4 to the 3, which, oh, okay. So this is a slightly more complicated example. I thought this is the one I drew here, but no. But you see. So the homomorphism density is roughly the subgraph density if the graph has lots of vertices, because almost all the mappings are going to be injective. Okay, so I'm also going to use the edge density throughout this talk. So what do I mean by edge density? So edge is basically this edge has 2 vertices. So by the definition, the edge density in a graph is twice the total number of edges divided by n squared, if n is the number of vertices in G. And when I say H is a small pattern and then G is the host graph, then I will use the notation THG to denote the subgraph density. So I'll just complete this example to keep the notation on the board. So in this example, the density is this number divided by number of choices of the mapping. Okay, so why homomorphisms is an important concept in graph theory? So it can encode lots of information. So for example, from Jack's talk yesterday, you could see that by using H as a cycle, it can encode the power sums of eigenvalues of the adjacency matrix for G. And by some other examples, if you choose G carefully, then it can be used to encode, for example, number of Q colorings of H, number of stable sets of H, and it can also be used to see whether the graph is Eulerian or not. Yeah, and then it has lots of other applications in general. So the homomorphism number and density, although it sounds, yeah, so besides this being a very natural candidate for some subject to study, they have lots of applications. All right, so I also want to kind of give some gentle introduction about graph limits. So before that, I want to motivate why we want to study graph limits. Practically, those are some important questions we would like to ask about large graphs. So for example, the first one is about property testing, which is a very active field in theoretical computer science. Is if you want to design fast randomized algorithm to tell whether a given large object has a property or not. So the graph property could be whether the graph contains a triangle, or you want to test whether the graph is connected or not, etc. And then the second one, which is closely related, is called parameter estimation. So you define some graph parameter, and then you want to give an estimation on that parameter without knowing every single adjacencies in the home graph. So these two are motivations more from algorithms. And there's also a very popular thread of research about how we should model how should we model large networks given some properties. So we have seen arbitrarily graph GMPs in many other talks. And there are some others which have been studied in, for example, social networks like the preferential attachment models. So those are 2 pictures that illustrate what are the graphs that are generated. So this is also related to graph limits and how we can generate a sequence of graphs from the limit object. So I call this generative model. And the last 4 questions are also closely related. It's about information access from this large network. So the fourth one is about how can we globally approximate a large network. So we want to get a compact approximation or description of this the large object, allowing some small error. And the fifth one is about sampling, as we just mentioned. So we can query those those little subsets. And from those sampling, how do we imply the information from the global of this global network? Okay, and then all these questions actually could be answered to some extent in the dense graph world by the theory of graph limits that has been developed recently. So I'm not going to jump into like two technical things about graph limits, but I want to give some visual motivations of why these make sense and then why some of them are not so obvious to define. So those are the pictures from Loa's book, Large Network, Graph Limits and Large Networks. So the first one, so there are multiple ways we can represent a graph. So for example, the first one is you just draw its adjacencies. It's the one we most commonly see. And second one is we can also write down its adjacency matrix. And the third one, which is probably is less common, but makes a lot of sense in graph limits, is translating from the adjacency matrix to its pixel picture. So what I mean is, so suppose the adjacency matrix is n by n, then its pixel picture is you cut the unit square. Oh, I just realized you couldn't see my mouse on this. Yeah, you cut the unit square into n by n congruent columns and rows, and then if it's 0, then it's a white box, and if it's 1, then it's a black box. So you basically draw this black and white pixel. So that's why it's called a pixel picture. So white pixel picture makes sense. It makes more sense when we are looking from far away. So for example, a neuroscientist, Jules, once asked a question. So he wants to understand how well human beings are able to distinguish random noise from some more structured pictures. So the left-hand side is the random graph G100 a half that we have defined earlier. So basically it looks like very chaotic in some sense. And for each box you draw here, then it kind of looks like uniformly gray if you look far behind. And the right-hand side is a chessboard graph, so it's very structured. So it's alternating between black and white. But the problem for this is if you draw some small rectangle here, it also kind of looks like uniformly gray. So he wants to understand whether human beings are able to distinguish these when n is very large. And then this is answered by Diaconis and Friedman. So they show they are not the same. Why is that? Because when n is really large, then we should expect this Ardigiani graph to converge to this uniformly grayish picture. However, for the right-hand one, if we reorder the columns and rows, putting all the even ones together and then the odd ones together, then this is exactly this chessboard graph. And it's clearly we can distinguish between this one and this one. And so their proof also uses something similar to to how we generate random finite graphs from the limit objects. So I'm just want to say that pixel picture could be helpful, but it could also be misleading in some sense because for graphs we do allow rearrangements, reordering of the columns and rows. Okay, so now let me give the mathematical definition of a graph limits. So a graphon, which is a generalization of graph in some sense, let's say it's a measurable symmetric function from 0, 1 squared to 0, 1. So in this talk, I restrict to 0, 1 squared, which is a unit square because of the pixel picture. But in practice, you don't really have to do this, do the unit square. You can generalize to other spaces as well. So for now, let's just think of 0, 1, the interval 0, 1 as the set of vertices. And because it's a function, so for each value xy, wxy is the edge weights between vertex x and vertex y. Let's just think of that way. Or in other words, you can think of this as a probability that there exists an edge between x and y. Okay. And so how do we define a limit of a sequence of graphs? So for some of the models, we can actually write down algebraically. So for example, if this is the preferential attachment model, and this is a finite graph we could generate from it, and then you can actually work out the algebra to see this is indeed this picture is indeed the limit object for this, and also it seems like this is the smoothed out version of all these discrete points. And then there are some other examples. For example, this is a half graph, which plays an important role in regularity lemma and logic. So basically, each vertex on the top is only connected to the vertices down, but to the left of it. And this is a pixel picture of this half graph. And then we could imagine when n goes to infinity, what's the most sensible thing to do to define its limit is to smooth out these squares into straight lines. Yeah. But what about for the sequence of graphs which are not really defined in such a concrete way? And how do we define its limits? And why those limits actually are helpful? So those are important questions. So basically, we want to understand why is the limit, how do we define convergence, and why they are helpful. Okay, so one thing we want is we want the arbitrary graph gn and half when n goes to infinity to converge to this uniform gray square. So that's the thing we want. So it turns out the correct notion we want is something called the cut norm. So a cut norm, so now assuming u is a function that you also allow to take negative values, otherwise this definition is very trivial. So what does it mean is you just find measurable sets S and T. So they doesn't have to be an interval, it's just measurable sets. And you look at somehow this rectangle defined by these two axes, and you look for what is the edge density, well, the number of edges between x and y, the weighted edge sum, and then you look for the maximum of all the possible rectangles you could get. So this is called a cut distance, and you could check that this is weaker than the L1 norm, and indeed, two arbitrary graphs will, with high probability, have distance theta 1 under L1. So that means L1 is too strong. But under this notion of cut norm, then the sequence of arbitrary graph will indeed converge to this uniformly gray constant function. So in the talk, I'll call this the constant function. And it also turns out by some earlier scenario, celebrated result by Chen and Graham, that this cut norm, which is only later defined, but we could trace back earlier, that this is closely related to the C4 density. C4 is a 4 cycle in this graph, and it's closely related to pseudo-randomness in this graph. Okay, and so I have defined homomorphism density to graphs. So now I want to generalize to graphons. So basically what you do is, this is a natural generalization. So when you're counting the density into a graph, you first see how those 3 vertices of the triangles are mapped to the vertices in G. So here you're doing the same. So you're mapping the 3 vertices of the triangle to x1, x2, and x3 in this unit interval, and you're multiplying all the corresponding edges that should exist. So this is a natural generalization, and you could also generalize from triangle to any graph H, and which is written down as this crazy interval, but it's really just the definition we're familiar with. And if W is the graphon corresponding to the finite graph, which is given exactly by this pixel picture, then this definition, homomorphism number to graphon, is the same as the homomorphism density to graphs. Okay, so it turns out, so what can we get from those limit objects? So the one most important result by Lorenz-Zagatti is that the space of graphons, when you quotient out by the 0 distance, is compact with respect to the cut norm. So why this theorem is very important? Because this one basically shows is equivalent to the regularity lemma. So it's actually equivalent to all the different versions of the regularity lemma, the weak one, normal one, and strong one. And it also means on the previous slide when I was asking those 5 questions, it shows the global scale, it gives you a global scale down version of arbitrary large graph. And another theorem is relating the convergence to the sampling, which says if for any convergence sequence Gn with respect to its cut norm, then the limit exists. So it shows the completeness in the sense that for any pattern graph F, the density of F to Gn will converge to the density of F in W. So let me just give this So this is a kind of the overall theorem. So basically, it says two graphs are close in cut distance if and only if their local sampling distance is small, if and only if their global approximation representation, difference is small. So it connects all the questions I mentioned earlier, except probably the generated model one. Okay, so these are the fundamental theorems in graph limits. And now I want to give another generalization to graphons, to kernels. So it's also not so much more different. So remember, graphons are functions with values in 0, 1, because you are generalizing graphs. So here for kernels, we just need bounded measurable symmetric functions where the range you're allowed to be any real number. So it can be negative, can be positive, it can be 100, it can be negative 100, for example. And you could consider kernels as limits of all weighted graphs when you're allowing arbitrary edge weights. So why kernels are also an interesting object. So because some graph parameters can only be written as densities to kernels, but not to graphons. Okay, so if you're bored of the talk, this is a quick exercise to check that if you want to count the number of Eulerian orientations in this graph, then it could only be written as a density to a kernel W prime. You couldn't replace this kernel W prime by a graphon. Okay, and also many classical extremal combinatorics questions can also only be rephrased as questions into kernels. So for example, the Ramsey multiplicity question I'll mention later is one of those examples. Oh yeah, the previous theorems will also extend to kernels when you have when you restrict the L infinity norm to these kernels. Okay, so what are the fundamental questions what are some other fundamental questions we want to ask? So first we want to, one very reasonable question we want to ask is which inequalities between subgraph densities are valid? So what do I mean? So here's an example. So if I care about graphons, so let's just restrict to graphons now. And now I care about the densities between an edge and a triangle. So in this grid, for any graphon W or any graph, I plot the x-axis will denote the edge density, y-axis will denote the triangle density. So for each graphon or graph, I can plot a point on this square. And I collectively get all those possible points, which represent all the possible combinations of edge and then triangle densities. Then I can get some shape in this. And what I want to understand is the boundary of this shape. So what are basically possible shapes that will enclose all the possible combinations. And it could also be generalized to many different patterns, not only triangles and edges, but this is the one we already know and it already took lots of efforts. So for example, in this case, we already know this boundary is y equals to x to the 3, 2. So what it means is we know this general theorem that the triangle density is at most the edge density to the 3 half. So that's what it means to translating from this curve to this inequality. And the second question is there a unified algorithm to prove these inequalities? And the third one is what are the extremal constructions? Meaning what are those points that are on the boundary? So by the compactness by the theorems earlier, we know all the boundaries could be achieved. So these cannot be achieved if we only restrict to graphs, but if we extend to graphons or kernels, these could be achieved. So for example, on this boundary, these type of graphons will be on this boundary, so they will be achieved. And this two-rank graph, so if you translate it back to graph, this is a two-rank graph, then it will achieve this 3/4 integral points here. Okay, and for the homomorphism numbers, they also play a role in database theory. So I'll just skip that for now. Okay, so we want to ask. So this is back is the first two questions. So which inequalities are valid, and is there a unified algorithm to prove them? So for now, let me just give a very simple example. So I want to understand whether for any kernel W. So remember now W can take negative values. is this inequality always true? Oh, any guess? Okay, I'll give you the answer for the first one since this is the first one and it's early in the morning. So the answer is yes. So simply you write down this definition. So if this point is x, this point is y, this point is y prime, then it can be written as wxy, wxy prime, and then do this. And then you can club this, so both of them are x, and then you have a copy of y to y prime. So you can rewrite this as an integral of a square. And then for sure, integral of square is always non-negative, so this is non-negative. And then maybe it looks cheating, but I could rewrite this inequality as this picture demonstration. So this is my wedge, this picture, x, y, and y prime. And I write this as a square when you fix s and then you copy y. So this is a square of this one. So this is a picture demonstration of this inequality. Okay, so by this inequality or its translation to this picture, we know this is true. Okay, what about the second one? So now we restrict to graphons, W. Anyone voting yes? Anyone voting no? Okay, so if no one votes no, then you guys are all genius. Yeah, so the answer is also yes. And it's actually an old result of Goodman. And he uses a purely combinatorial way to proving this, but secretly this is also like a Cauchy-Schwarz inequality. And this is exactly this is part of the picture I showed earlier. So this curve is this inequality over here. And we can see the valid set of points lie right above this curve with those points intersecting. So this inequality is true. And since I mentioned Cauchy-Schwarz inequality, and you could write, yeah, and indeed you could do that. It's not so obvious for now, but you could write this inequality. So if you move the right-hand side to the left and you want to check whether this inequality is at least 0, then the left-hand side, it can be written as this sum of square. So I'm not really defining what's happening here, but there's some gluing algebra when you're working with graphons that allow you to get this sum of square. And you can already see, like here, I only have 3 terms, but now in the sum of square, I have a lot more terms. So maybe things is slightly more tricky when we are trying to search for this. Okay, what about the last one? So now I have this huge inequalities. Now I want to work with kernels. So is this always true if I plug in any kernels W? Okay, well, since the first 2 are both yes, so the last one has to be no. Yeah, and the answer is no. And I cook up this example from Ramsey multiplicity. So this answer is yes. Sorry, this answer is no. So there's are examples of W where this inequality fails. Right. So in general, we can see like it seems like at least for these examples, one could get a pretty complicated sum of square in order to proving this example. And indeed, it was a question asked by Lovász and Rasborov, who was the father of flag algebra in all these type of inequalities. They asked whether there's a systematic way to prove graph homomorphism density inequalities. Oh, okay. So the question is framed into polynomials, but it could easily be seen that we only need to care about linear inequalities because because if you do 2 disjoint union of if H is a 2 disjoint union of 2 different graphs, then the density is a product of these. So we could only So linear is enough. And for graphons, the earlier result of Lovász and Szegedi, they show somewhat positive towards this answer. They say every graph homomorphism inequalities into graphons, if it is true, then it could be expressed as an infinite sum of square. Or in other words, so what do they mean is for any epsilon, there exists a sum of square so that the difference between this inequality and this sum of square is only is an L1 distance at most epsilon. So it could be approximated by finite number of finite terms of sum of square. But is that really like a finite sum of square? So unfortunately, this is proved in this breakthrough result by Hatami and Norin. So they showed if we want to understand graph homomorphism densities into graphons, then this question is undecidable. So what does undecidable means is that is even stronger than this. Is there's no algorithm that will terminate in finite amount of time that could always output the correct answer, whether the inequality is always true or there's a counterexample. Yeah, so in particular, it shows we couldn't always do a finite number of semi-definite inequalities. Okay, so what about kernels? So as we've seen, like kernels, you have a lot more flexibilities. So it also seems like it's easier to fail. But does that also mean it's easier to verify if some inequality is true? So I just want to give some of one beautiful conjecture by Lovász I really loved. So this is a positivity graph conjecture. So he asked, the conjecture is if the density of some graph H, so if I plug in any kernels W, its density to any kernel W is always non-negative if and only if H is a square. So here again, square means H can be written as a square of another graph. It doesn't mean the C4 cycle. Yeah. So if this conjecture is true, it means checking these type of inequalities true or not for kernels is a very simple decidable question. We just need to check whether H itself could be written as a square of another graph. Well, this conjecture still remains widely open. Okay. So Lovász has asked explicitly whether any valid graph density inequality into kernels could also be certified by sum of squares. And it was proved by it was disproved by me and my co-authors, Blackerman and Remount. So we show that it is undecidable again. So so basically, there's no hope to get an algorithm that is guaranteed to terminate in a finite amount of time to tell you the correct answer. So in particularly, it shows, from our proof also, we have examples of such valid inequalities, which are always true, but cannot be written as sum of square. Okay, so how do we prove undecidability? I mean, it traces back to proving the undecidability for inequalities into homomorphism numbers, and was also used in the previous work by Hatami and Lorraine. So we basically reduced to Matias-Chavez solution to Hilbert's 10th problem, which says it's an undecidable problem whether an integer coefficient polynomial is always non-negative when you plug in integer values into the variables. So we know we should reduce this, but how do we actually carry out to the densities? I mean, the crucial thing is for densities, the density can be a fraction number. So we have to somehow work out those integrable points in the in some allowable ways. Okay, so this is the first half of my talk. So it basically shows if we want to prove in general these theorems into kernels, then this question is undecidable, which is probably also a good news for mathematicians. It means there are more things we could dig out and then see what are the interesting things about this and what is the other information we could extract. Okay, so the second part is about the third question, what are the extremal constructions? So remember those curves I draw, so we want to ask what are the possible points that lie on the boundary? Okay, so there are many candidates of those extremal configurations. So let me just pick the simple one, like the random construction. So we probably also see earlier, like in the Ramsey theory talk, like whether the Erdős-Rényi graph is the extremal configuration for Ramsey numbers. So here I'm looking at the generalization of Ramsey theory, but in a very different scale. So this is called the Ramsey multiplicity question. So here I'm just giving the definition for triangles, but you could easily generalize to any other graphs. Okay, so what is Ramsey multiplicity? Again, you're two coloring this graph, the host graph. This is G, but here's W, is the same. You two color it, and so you have a red subgraph and then a blue subgraph. And you want to add up the red triangle density and the blue triangle density. So translating to the graphon version, so you have the red subgraph corresponding to graphon W. So the blue one is 1 minus W. And then you want to add up the density of triangle in W and then the triangle in 1 minus W. And now, because I work with graphons, so you could see I'm actually looking for the range in the host graph when the number of vertices goes to infinity, while the pattern is fixed size. And then I want to ask what is the minimum density that I could guarantee. Okay, so what is the random bound? So if I plug in W to be the random construction, what do we get from here? So this is a very simple linearity of expectation, as we have seen in Hui's talk yesterday as well. So I consider this constant function W equals a half, or which corresponds to the limit object of arbitrarily graph G and a half. And so for each triangle, the density into this constant function clearly is 1 over 2 to the 3. And I have both W and 1 minus W. Both are a half, so I multiply by 2. So this answer is 2 times 1 over 2 to the 3. So I call this the random bound. Okay, so since I get an instance of W where this quantity is 2 times 1 over 2 to the third, it means this bound is an upper bound for this infimum. Okay. So this random bound gives a very simple upper bound for this question. So we want to ask, is this also a lower bound? Or in other words, is this random construction optimal? Okay, so rephrasing back, so if we want to also understand whether this is also a lower bound, we want to ask for which graph H, the density of the red density of H plus the blue density of H is at least this random bound. Here I'm just replacing 3, which is the number of edges in the triangle, by the number of edges in H. So basically the question is whether the random bound is also a lower bound. And Erdős calls such graph a common graph. So if this random construction is sharp, then it's called a common graph. Okay, and if you expand these things out, you could see the left-hand side could actually be written into a linear inequality to kernels. So that's why kernels is also an important concept. So basically here we're trying to study explicit linear inequalities into kernels. So here is the question again. We want to see whether Erdős graph is the lower bound. And this is closely related to Sidorenko's conjecture. So Sidorenko conjecture that if my graph H is bipartite, then for any graph on W, the density of H is always minimized by this constant function. So remember, TK to W is just the edge density. So the right-hand side is exactly the density of H into the constant function. So why we need the graph to be bipartite? Because it's easy to see if H is not bipartite, I can choose the host graph to be. So if H is non-bipartite, then if W is bipartite, then the density on the left is 0. So clearly this inequality doesn't hold. So it only makes sense to asking for bipartite graph. Okay. So forget about H being bipartite graph. Now let's just look at this type of inequalities and why this is related to these inequalities. So because if this inequality is true for some set of W, then when you add up THW plus TH1 minus W, which is the left hand side here, if this inequality is always true, then this is at least P to the EH, where P is the edge density TK to W. And then the right hand, the second term is at least 1 minus the P to the EH, if this inequality is true. And then by convexity, this is at least this red bound we have over here, which is a definition of H being common. So it means like Sidorenko's inequality. This type of inequality is in some sense a stronger version of the Ramsey multiplicity question. And we can show that H is Sidorenko if and only H is Q common for every integer Q. So Q common means so common graph is 2 common because you do 2 colorings, red and blue, and then here Q common means you can allow Q different colors. Okay, so just come back to this questions of which graphs are common. So so it turns out most graphs are not common. So it's a very unfortunate naming for this class of graphs. And it has been shown that every sparse graph with chromatic number at least 4, for example, every graph with chromatic number at least 4 is not common. And it has been like a series of work, and the list goes on and on to generate graphs which are non-common by using many different beautiful methods. So here I just list some of them, and then some of them also share with the common ground with studying pseudo-Runkel's conjecture. Okay, so we know that the set of graphs which are not common is so huge. So basically, it means the graphs which are common are like a small subset. So can we get a handle of those graphs which are common? So can we say anything about them? So give a full characterization, meaning give a full list of the graphs which are common. It seems to be at least completely out of reach for me. So a different question we can ask, is there some determining factor? So is there some graph parameters that we know if passes some threshold, then we know this graph has to be common or not common? Okay, so here's a Ramsey multiplicity question again. Let me take back a bit. So remember here that we know if the graph has chromatic number at least 4 and is very sparse, then the graph is not common. So maybe chromatic number can play some role here. And then also in this paper, Jagger, Stolvashek, and Thomason, they showed any graph containing K4 is the clique on 4 vertices, is not going to be common. Then K4 has chromatic number 4, so maybe 4 is some magical number here. So what can we say? Well, so pseudo-Runkel's conjecture about arbitrary graphs, so those are chromatic number 2. So all the progress by the relationship I showed earlier, all the progress are done through the pseudo-Runkel's conjecture. And what about graphs with chromatic number 3? So those have been shown to have, common graphs have been constructed for chromatic number 3 by many authors. And the progress has stalled for some time until only in 2012 by this group of people using Flock algebra, meaning computer-assisted way, to construct a graph on six vertices with chromatic number 4, and that graph is common. And then we basically don't really know much beyond that. So the chromatic number 2, 3, and 4 has been done, and we also know when the chromatic number is larger than 4, and if it's very sparse, then it's definitely not going to be common. So this question has been asked by different groups of people, like is chromatic number a determining factor? Meaning, in particular, is there any common graph of chromatic number 5, say, or is there some finite constant k when the chromatic number passes k, then the graph is not going to be common. And we also answered this question negatively. So we showed that for any number k, there actually exists a graph with chromatic number at least k that is common. So chromatic number is not going to be a determining factor for the commonness in Ramsey multiplicity question. And our method, in some sense, is somewhat different from before in order to do these constructions. So we didn't use any computer-assisted proof, for example. So the new perspective for this problem is the so-called local versus non-local approach. So this type of approach is allowed in other problems. And so what it means is if we perturb the conjectured minimizer, which is the constant function, what happens? Or to be more concrete, a subset of this question is the constant function a local minimizer? Okay, so let me define this more formally. So without loss of generality, let me just fix the H density P to be a half for now. So I say H has the local pseudo-Runkel's property with respect to the cut norm if there exists an epsilon, which considered as the radius of the neighborhood, such that, I don't know why it's auto displaying. Okay, so such that the density of H so the desired inequality always holds if we are looking for the epsilon ball around the conjectured minimizer, the constant function a half. So the most important condition is I need the graph on W to have distance at most epsilon from the conjectured minimizer. So it's within the epsilon ball. And secondly, to be fair, I want to restrict to the graphons to have density a half for a fair comparison. Okay. So basically, it says it has a local Steranko's property if there's a universal radius epsilon where this general this inequality holds. So I don't want, in particular, I don't want this radius to depend on the direction I'm going from this conjecture minimizer. So I want all different directions to have the same distance. Okay. So Lovaas is the first one studying this local Steranko's property. So he showed that H is bipartite, then it has the local Steranko's property. So in particular, it doesn't disprove Steranko's property, because if we know the constant function, if the constant function is not a local minimizer, then it's not a global minimizer. It means Steranko's conjecture is false. But he showed that in fact, Steranko's conjecture is true locally when H is bipartite. Okay, so we want to understand what happens when H is not bipartite. So in fact, we could give a complete characterization as a joint work with Jacob Fox. We showed that the local Steranko's property holds. The local Steranko's property holds if and only if basically H is a forest or the girth is even. So it only depends on this graph parameter of H. So in particular, this includes the bipartite graphs H, because it doesn't, because the shortest cycle is length 4, or is the forest. So it extends, so basically it means we kind of understand everything locally around this conjecture minimizer. So we understand the things locally. So how do we use this information to get the global picture of this inequality? Okay, I forgot to mention that if H has odd girth, then the constant graphon is a saddle point, so it's not a local minimizer. Oh, okay. Before that, no, sorry. The proof starting point is again you expanding out the desired inequality into the main term and the error term, and when you expand this out, you could see this is linear inequalities into this kernel U, because you could take negative values on its entry, and the question is whether this linear combination is at least this desired value. Well, we just showed earlier that this type of, in general, this type of question is undecidable if you want to prove every single such inequalities. But for this particular inequalities, because this looks very special, like for the coefficients. Oh, I forgot there's coefficients somewhere here too. Then we could show, we could prove this theorem. Okay. Right, so now the question is, how do we patch these things together? So if we know the local information, how do we infer that to the global information? So to prove our theorem, the existence of a common graph of large chromatic number, what do we do is, in the non-local regime, when the distance between W and then the constant function, when the cut norm is large, we use the convenient relationship between the cut norm and then the C4 count. And when the C4 count, so basically it means the C4 count is at least some bound in terms of epsilon. And in particular here, crucially, is the fact that epsilon doesn't depend on the direction. It only depends on H. Okay, so when the cut norm is large, so we can bootstrap the fact that the C4 count is large, for example, by patching a large complete graph. Okay. Oh, sorry. Let me take it back again. So what I mean is, so if the C4 count is large, then when you're counting the density of a complete KNN into this graphon, then you know the C4 count gives you some oops, what happens? Okay. Then the C4 count is 1 plus this epsilon to some power in terms of n squared. Okay, so that is some polynomial gain we could get in terms of n. Oh, sorry, not polynomial. The exponent is n squared. Okay, and then hopefully, yeah. So it sounds like we have gained quite a bit. But then there is some difficulty when we are patching the local and non-local together. So what do I mean by patching? So we first, by the result of Erdős, there exists a graph with high chromatic number and high girth. So in particularly, we can find a graph with even girth that is common, but with high chromatic number. So let's say that graph is H, and then we patch H with a large complete bipartite graph. So the hope is that we know in the local world, H is fine, and complete bipartite graph is also fine. In the non-local regime, I don't know much about H, but I know I could gain a lot about the complete bipartite graph. So I'm hoping that the gain I could achieve from the complete bipartite graph could offset the potential loss I have for this fixed graph H I was given. But it's still, there's some challenges. Because as I said, how much we could gain from this non-local regime is basically 1 plus epsilon to the power of n squared. So think about, we just want to compare that with 1. So now what we gain is 1 plus epsilon to the n squared. And so if we want this to really work out, so we need this epsilon to be like a polynomial in some sense, like 1 over n squared or some poly in n, in order for it to work. So I need that epsilon to be decently large in order for the non-local regime to work. However, for the local regimes, so for the characterization theorem we could get earlier, the bound we get is only exponential. Is exponential. So in the sense that the epsilon ball, I could guarantee H plus this complete bipartite graph to be locally Sidorenko is only if epsilon is smaller than some 2 to the say minus n squared. So that is much smaller. So it seems like I couldn't really patch these two things together. So it turns out there's lots of technical difficulties actually to remove the dependence on n in the local regime. So that consists of like a huge chunk of the technical difficulties in this paper, just to remove the dependence on n for this local world. And also, if we want the graph to be connected, somehow I just don't want a disjoint union of this H and this complete bipartite graph. And so, I mean, the simple way to connect them is to use a long path to join these two parts. But the problem is if the path is too long, then it will break what we gain in this non-local regime. But if it's too short, then it couldn't really break the correlation of H and K. So yeah, so there are some technical subtleties in order to find the correct range of the length in order to connect this and then to analyze this carefully. Okay, and then so in general, our approach, this local versus non-local idea, and then how do we actually remove the dependence on the size of the family in the local world helps also understand making progresses in some other conjectures as well. Okay, so in summary, those are the 3 questions I'm very interested in, and then there's still lots of open questions left. In particularly, we know it's undecidable if we want to prove such general inequalities, but what if we have some restrictions on these inequalities? So one simple restriction we could have is what if this inequality only has 2 terms or 3 terms? So you could consider Sidorenko's conjecture to be an inequality in only 2 terms. And so we couldn't prove at all whether such problems, like inequalities into only 2 terms, is that decidable or not. So and that, I think that's a very attractive question, at least for me. Okay, yeah, thank you everyone for your attention, and then I'll conclude my talk from here.
Thanks for the very interesting talk. Are there any questions?
Sorry, can you go back to the definition of the kernel?
The what?
The definition of the kernel.
A kernel. Okay, let me see. Is there a way to do it faster? Or is this way faster? Not really. Okay. Yeah, kernel are basically bounded measurable symmetric functions from 0, 1 squared to R.
Yes, but I found this kernel is quite arbitrary. I mean.
Yeah. I'm still not there yet. Sorry, it probably takes a while. Yeah, but yeah, it's just a general. Oh, I think did I pass it?
Passed.
Already
Later,
passed it?
later, this is graph.
Oh, okay. Yeah, this one.
Yes, I found how it contains the general properties of these graphs, and also as you said, the order of the label of each vertex is different, and if you change the order of the vertex, then the kernel or the graphon will change, right?
Yeah, exactly. So I lied a little bit when I was talking about the distance between two different graphs or kernels. So yeah, exactly as you said, because the order matters. So when you're doing this cut distance, it's actually up to the measure preserving maps from 0, 1 to 0, 1. So you allow all those reordering.
So in the following inequalities, if there are some small changes, because well, consider a limit, maybe some change of label will still have a limit, but a different limit, right?
So for you, sorry, what do you mean?
So anyway, it is just a measurable symmetric function, and there will for the same graph, are there always the same limit for the measurable symmetric function?
For the same graph?
Yes.
Yeah, because you allow the permuting the limit object as well.
Yes, I mean,
yeah.
After permuting, will the kernel change?
Yes, because the value will change up.
Yes,
to
and
the
even the kernel change, the following inequalities for the t are still the same.
Yes.
Oh, okay.
Yes.
Thanks. Quite
If
interesting.
I understand your question correctly, yes. I think the answer is yes. Yeah, you oh, I thought you asked the first question too.
Yes, I think that's my question. Just yes, a bit quite confusing about what's happening.
Oh, okay. Sorry.
Are there any other questions?
If there is a sequence of graphs converges into a graphon of in the cut-norms sense, then for the uh, homomorphism density, will this homomorphism density for the sequence of graphs converge into the
Yes. You also convert to this. Yeah, it's a theorem I showed here. Yeah, this one. Yeah, so if so, you can replace this by Wn. So if they are convergent, then this density will also converge. Yeah.
Okay.
Is that your question? Did I answer your question?
Yeah.
Okay.
Are there analogs of the positive graph, zero-rank-goal, or common graph conjecture where you replace the edge on the right-hand side with a more general graph? So your inequality between homomorphism count of H and then homomorphism count of some other H prime.
Yeah, I think there are lots of such work, in fact. And like a norming graph, I guess you're also familiar with, and weakly norming. And then there are also some questions about, like, if I compare two different graphs, like H1 and H2, and I want to understand like exactly this envelope, like what is the correct exponent on the right-hand side. So I think that is also a very attractive question.
I want to know what's the advantage that we construct such limit with respect to normal graphs when proving this theorem?
Yeah, great question. So there are different aspects. So one maybe like the most okay. One of them is like when you're working with a limit object, you don't have to deal with the little one terms. For example, it's about this proof. And also I forgot to mention, maybe I should have. So all these theorems are proved in a purely analytic ways. But the regularity lemma originally by Samaretti was proved. You probably heard that in Sarah will talk this afternoon as well. Yeah, you probably mention it. And then so that is proved in a purely combinatorial way. But somehow it seems like there's this parallel proof using purely analysis, and it's giving the kind of giving the same thing, and then also in some senses it shows all these different like a power of this regularity are the same. So yeah, you can show the compactness is equivalent to the weak regularity lemma, and it can be used to prove the strong regularity lemma, which can also be used to prove the normal Semiratis regularity lemma. And yeah, and also there was lots of general theorems proved before. For example, there was a Noga et al. They proved there was a full characterization of which graph properties could be tested when you only query constant subset of vertices. So they gave a full characterization of such that thing, and then it was as a parallel development, this combinatorial proof was also developed into this analytic proof. So they use purely graph limits language to give a full characterization as well. Yeah.
Thank you.
Any other question? Okay, if not, let's thank the speaker again.